เดี๋ยวผมเปิดไฟ Okay, yeah, so we just discussed about homework. So we were talking about density operators, which is a sort of a new way to think about quantum states. In particular, we call everything that that can be written as a vector like this a pure state. Right? So quantum state, what we knew as what we call quantum state before, quantum vector, state vector becomes a pure state, and there is a different class of states called mixed state. So this is a pure state. And in general, a state is a convex combination of projector, one-dimensional projection operator, which, well, we think of this as so for pure state there will be only one non-zero term in the sum, right, which is the state vector, the outer product of the state vector itself. And we talk about it a little bit about the meaning of this. I don't remember if we talk about the probabilistic interpretation before, in the sense that if จะเริ่มสกูล if I want to find some average or expectation value of an observable O, then this is the expectation value. So have we derived this? Probably not. Yeah. So be an average of an observable if we are uncertain which pure state we have. Right? In our hand, in the sense that I, the receiver, assume that I would get, there's a different probability of getting some different pure state, right? And then usually this set is called an ensemble. Yeah, similar to how we use the word ensemble in statistical physics. So here we assume that the scenario is that I have some pure state, but I don't know which one, and I have assigned some probability to each pure state. If this is the case, then of course, when I want to find the expectation value, it would be a weight average of the expectation value in each pure state. And by the way, if you want the probability of getting some measurement outcome, then I can replace this by projection operator corresponding to eigenvalues of that that observable, right? Oh, this is what I want to get, not what I should start with. So average. Oh, let's call it, yeah, the average of the observable. Well, this should be the average of the observable in that pure state, and then weight by the probability, right? Which is this. And then I can rearrange this. Because the observable is the only part that is not does not depend on k. So first I can write the inner product as the trace of an outer product. And basically, this is just the density operator. So actually, this is sorry, another way to motivate density operator directly from just how we calculate expectation value in quantum mechanics, and then they're basically just a common statistical sense, right? That this is how we average things. And so you can think of a density operator as a tool to calculate probabilities. However, as we discussed before, this so the way a way that in which we write or we decompose rho into an ensemble is not unique. So in general, unless there is only one term, that is, unless rho is a pure state, there would be more than one way to write this as other ensemble, right? Decompose it using other ensemble of pure state and other set of probabilities. So each way that we do this is called an ensemble decomposition, which a lot of time I will just abbreviate as just ED. Yeah, I think today, today we'll look further into this, into how different ensemble decompositions are related. But this is sort of easy to see in the case of qubit because we have the block sphere picture. Let's see. Do we have to say something before that? I think before we get to the specific case of qubit, let me clarify or make some further remarks about the characterization of density operator that we started last time. So I think last time, okay, I don't remember how I write the criteria for rho to be a density operator. But let's say today, maybe if and only if, but there are different characterization as well. So maybe one that I put out last time is that it is Hermitian, and it is positive, but I would say that since it's Hermitian, then it means that I can diagonalize and then give set of eigenvalues, right? So then I can say that the each eigenvalue is non-negative, and lastly, the trace of rho is 1, but the trace is just the sum of the eigenvalue. So well, in this case, so the eigenvalues also act like probabilities, of course, because if when I diagonalize rho, it means that I have another ensemble decomposition in which the eigenvalues are the weight here, and then and the eigenvectors are all play the role of the pure state. But that is quite a special case because the eigenvectors of Hermitian operators are orthogonal, so you can choose them for them to be orthogonal. But in general, in an ensemble decomposition, these psi are not necessarily orthogonal. So the sum is can range from anywhere from 1 to infinity, basically. And maybe I mentioned that that we don't really need the first condition. Well, so I think that's one thing that we can try to derive now. So let me define a positive operator, that rho is a positive operator if and only if when I sandwich it is always non-negative for all state in the Hilbert space. So if rho is diagonalizable, then that means always eigenvalues are positive. But here I have not said whether rho is Hermitian or not. It turns out that in complex Hilbert space, so if H is some complex vector space of dimension D, then being positive, rho being positive implies that rho is also Hermitian. And in particular, this is true R. For example, basically, I think any anti-symmetric, well, I can, yeah. If I sandwich it with any real vector, then I get 0, basically, and well, but if you can put in complex vectors, then you will see that yeah, that, in some case they'll get you get a negative number. It's from I times I. So in real vector space, there's not enough in a sense there's not enough vector for this statement to hold. So proof, actually there are two. Well, there are multiple proof. Different way to show it. I think one easy way is that, so let's say proof one. Remember that rho is not necessary Hermitian, right? A priori, when you read my textbook, sometimes you see this word, right? So it means that we said it doesn't have to have some property, even though we will prove that in the end it must have some property. So we just don't know it for now before proving it. So every vector, every operator. So let's see. So rho, yeah, let's just use a symbol for some generic linear operators. So I can decompose it into real and imaginary part, where H and G are both Hermitian. So now if I, since G is Hermitian, so we want to somehow get rid of this term, right? Since G is Hermitian, I can choose to look at the basis of eigenvectors of G. Let's see, G, J. So now if I sandwich the whole equation, and this would be the jth eigenvalue of G. But since G is Hermitian, then this must be real. Right? But then if we think about the hypothesis, right, that that A, we are starting with the fact that A is positive. So this whole thing must be some real number, is forced to be a real number greater than 0, and so you cannot have this term basically because the I here. So there is a different way to prove this, which is a bit more complicated, but maybe I should do it anyway because it's a common trick in linear algebra. Okay. How we know that J is because G is Hermitian. It's like in quantum mechanics. Eigenvalues of Hermitian operator are always real. Yeah. So it's precisely because it's not this real and imaginary part are not just some arbitrary matrices. They must be Hermitian. Now I apologize because I have to look up my notes. So second proof, uh, is a bit more complicated, but it has some nice ideas in it. So basically, from the definition, since this is a positive number, is there any question? Okay. So since this is a positive number, it must be real, right? It means that if I take the complex conjugate of this and then use the bracket rule that we know, I would have that this is equal to that, right? Or let's say, so yeah, I think the better way to do it is that if I take the dagger inside, this is equal to taking the complex conjugate of the whole thing, right? But then since this is real, then these two must be equal. And so at least we know that on the diagonal, so when we sandwich it with the same vector on both sides, this has to be the same. So you might have hope then that, okay, somehow then because of this, maybe we can use it to show that it must be row and row dagger must be the same, must act the same if you have off diagonal terms too. So does this mean that row equals row dagger? And the idea is, well, it turns out to be true. The idea is usually called polarization identity. So what we are going to do is that we want to show that it follows from that this inequality for diagonal terms also imply the equality for the off diagonal term, which sounds a bit suspicious because basically we are trying to use a special case to prove the general case, right? But the freedom here that we have is that I can put any linear combination. I can write psi as some parameterized linear combination here. So that's what I'm gonna do. So this is if I have defined psi to be a linear combination of two vectors. So on the one hand, if I choose choose it to be a uniform linear combination. So here I don't care about normalization. We're just working in some vector space. I would get, well, this is just a calculation, right? I get diagonal terms, I will get off diagonal term. I'm sorry, sometimes psi and phi might look a bit similar. Okay, my Obsidian notes when I export it to PDF doesn't label equations, so it refers to some equation that I don't know where it is. So let's see. Right. So if I take the complex conjugate, so let's say this is equation 1, and then I take complex conjugate of this equation, then everything that I have, so the diagonal term will be the same, right? But for the off diagonal term, I have a complex conjugate. And then subtract the two together. Subtract this guy. Well, basically, I would get that the off diagonal term, the sum of them are the same. Once I take, even if I take complex conjugate, right? Okay, now we just leave it there. On the other hand, I can choose different linear combination. So maybe one of them is I. Yeah. Alpha is 1, beta is I. Then I will get something like this. And then we do the same. Where just psi and this psi are different, right? Because I choose different parameters, so I cannot just subtract them and get 0. But I can do the same, taking complex conjugate of this to get another equation and subtract those two new equations. And then I would get that. Now we have these two equations that we want to compare. Right. So if I now add them together, yeah, I'll Q this term, I'll Q that term, and what is left is just one term, right? So it will say that this term is the same as its complex conjugate. Well, not its complex conjugate, but here if I do the complex conjugate again, then I get this, right? And so therefore, if this holds for psi, then it holds for off diagonal matrix elements too. Nice. Any question? I can leave this. Yeah, alpha and beta can be any number, right? You just have to find some way to get out the off just one off diagonal term. Yeah. You there are a lot more freedom, right? But you just need you don't need more than this. Maybe does that answer your question? Well, just that if I choose it to be just one specific value, then I cannot prove anything, because we just live with like we are left with just the same statement. So then, because of this, of course, I just show you because this is some linear algebraic trick, but we just prove it in the first way. We just prove it in a totally different way, right? But either way, now I can reduce this. If we want to, we can reduce this to saying that rho is a density operator in complex Hilbert space. If and only if, and then now I can just erase the first property, right? And then says that rho is positive. So we use this sign is a matrix inequality. Right. And then the trace of rho is 1. And really this is just because since any ensemble decomposition, the weight in ensemble decomposition has to be probability, right? Has to be real, has to be positive and sum to 1. In particular, it must be the case for the when you diagonalize for the eigenvalues of the matrix as well. So this has to be real. And so this is sort of the most general way that you can generate probability measure from Hilbert space, because the only constraint is just that probabilities are non-negative and sum to 1, right? Good. What was I gonna say? Oh, so just a remark. So this way of writing things. So at some point, you might see some statement like the matrix A is more than or equal to B. And really what that means is that the difference of A and B is a positive operator. And here the property of, or the definition, the actual definition of positive operator would be important, right, to remember, because A and B may not be Hermitian. So and in particular, even if they are Hermitian, they may not be diagonalized in the same basis. So this does not mean that eigenvalues of like A minus B is positive, because you may not have eigenvalues. Okay. It's really just mean that what the definitions say, that this is non-negative for every sign. Now for qubit density matrix. Oh, okay. Okay, maybe another question is, well, how can you check whether what's the difference between pure state and mixed state that you can check? So here by mixed state, I mean that states that are not pure. And we just sort of discussed the meaning of why it's called mixed state last time, right? Because it's kind of like you have uncertainty, you have so convex combination. Another name people say is a convex combination are mixtures. So this is like mixture of pure state, but of course we talk about, and we will see in a minute that you don't have a unique mixture for each row if it's a pure state. If it's a mixed state, of course. If it's a pure state, there's only one ensemble decomposition that is You have probability 1 on that pure state, right? So characterization. So from the definition of pure mixed state, right? It means that if you, so let's say you look at eigenvalues. If you have a pure state, it means that you only have one non-zero eigenvalue. Right? Just correspond to this projector. One non-zero eigenvalue. The rest of them are zero. And there's like 15 different ways to say the same thing, right? It's like the support of rho is one-dimensional. That is the space that is project onto is one-dimensional, or rho has rank 1. Do you remember the definition of rank for a matrix, which is different from rank of tensor? Every matrix is a rank 2 tensor, but we don't use that here yet. But rank here is that it's either the number of linearly independent rows or linearly independent columns. Yeah, there may be other way to say the same thing. But when we have more than one eigenvalues, there's some nice way that that you don't need to check every eigenvalue to do this, because of the constraint that the lambda has to be probabilities. So the normalization come into play. So for example, for pure state, you have that trace of, or let's see, rho is equal to rho squared. Right, because of course this is one of the necessary property of a projector, and pure state says pure even only if it's a projector, and rank 1 too. So you can test the pureness by multiplying the matrix, or actually it is true as well that for pure state, if you take the trace, and this is the same. And this is basically, so you can try to derive this yourself. It's basically the fact that unless the probability distribution is deterministic, so like just one outcome and rest is 0, then when you square all of them, and the sum of them, it gets smaller. Yeah. So in general, this is less than the trace of rho. In general, it's less than or equal. If it's a mixed state, then it's less than 1. And in homework 3.1, you will prove that this condition also force rho to be a pure state projector, even without having to assume that rho is Hermitian or positive. And well, I think this is part B. And the part A is that if you assuming just this and not that rho is positive, well, or say in other way, if you assume just this, then it does not imply that rho has to be positive. So yeah, so one part is to show that this is not sufficient condition. Yeah. Okay, good. Now talk about qubits, density operator. Uh, can you recall the form of, or can you recall the eigenvectors and eigenvalues of a general Hermitian operator for qubits in the Pauli basis? So at some point we talk about it in the Pauli basis just because we know really well about the eigenvalues and eigenvectors of Pauli's, right? And I mean, by when I say Pauli, I also mean this guy, just like Pauli in different direction, because they all have plus or minus one eigenvalues. And the eigenvectors are, so for the plus one is just, well, not talking about projector yet. For plus one is this guy, and then for minus one eigenvalue is this guy, right? And so we have that, I can leave it here. Chop ไม่ไหวมากเลย So general 2 by 2 on qubits, Hermitian operator. We have proved elaborately that the identity and the Pauli matrices, the three Pauli matrices, form a basis of the real vector space of Hermitian operators. So if I have an arbitrary Hermitian operator, then I can write it as yeah, just to remind ourselves, right? Which then, if I pull out the magnitude of that three-dimensional vector, then I would get that oh, sorry, no, this is n. Let me check the size here. Right. So here the information about eigenvalues and eigenvectors are shown to us in the full view, right? So these are the two eigenvectors, and these are the eigenvalues. So then what would be, if you apply this to to the general density matrix. So if I assume that rho is positive and has trace 1, right? So what would be the general form of a density matrix? Do we know A naught? Not one? And what do you think it is? So what are the conditions? What condition is here, right? So what does this condition imply? This is for qubits, right? Like a single qubit. Yeah, so what happens if you take the trace of this guy? Yeah. Yeah, the Paulis are traceless, and the trace of the identity is 2, right? So A naught is 1/2. Right. And then what about what about this vector? Now we have to use the first condition, that the eigenvalues are non-negative. Well, so this is 1/2, right? And so the magnitude of A has to be less than 1/2, right? Right. Or at most 1/2. So if I do this, sorry, then I can write like this, where the magnitude of this is between 0 and 1. So now we can draw the new block ball, which is where the surface is identical to the block sphere. So we are in, if I want to visualize this, then we are in 4 dimensions, right? 4 real dimensions. But since the A naught is fixed to be 1/2, so we sort of imagine first imagine the blackboard to be 3 dimensions. And then imagine that in that 3 dimension is a subspace in which A naught is 1/2. So we just, yeah. So now, let's say if I just think about 2 dimensions of this, so yes, can be anything xy. Then the condition here, so this constraint is the magnitude of the vector, right? So it means that you have everything within this circle is fine. And then when you pop it up to the 3 dimension, you get the block sphere, but not just the surface, right? But also inside as well. แต่ก่อนผมเคยวาดทรงกลมได้หรือเปล่าแต่นี้วาดไม่ได้แล้วอ้วนๆทุกทีเลยสงสัยจะไปกดกระชาที่เป็นไข่มากเกินไป There's one. Right. Yeah, so now with this new picture, then an arbitrary density operator is still represented by a vector in this picture, right? Except that now the vector doesn't have to be at the sphere, at the surface of the sphere. So the length is just whatever the length of this vector is, which we call block vector. Any question, comment? Mhm. So maybe here, before going to prove some theorem to finish this part off, we can revisit the axiom of quantum mechanics again. I don't know what this version this is. It's like version 1.2, 1.5. It's not complete yet, right? This is like 1 point something. Because now our axioms sort of have changed, right? We have generalized objects in our theory. So here, a state, so let's say a state is represented by, or state of system is described by a density operator, rho. So what happens when you make the measurement? This is kind of trivial, right? That the state, well, let's say if you make a measurement corresponding to an orthogonal basis, or yeah, sorry, we have already sort of talked in a generalized way, is that measurements correspond to orthogonal projector. And sum to the identity as well. Yeah, so this is just to be a little bit more general than projective measurements, right? Here you can have degeneracy. In other words, each projector can be more than one dimension if it's degenerate. Well, then the probability of getting an outcome J is as we sort of demonstrate, but there we did it with an observable instead. An observable is just the weighted sum of projectors, right? Weighted with eigenvalues. So here, oh, there's already the result that we want to get. This is probably of outcome J, right? And then the state is changes. So for the state vector, I would just apply the projector and then normalize the state, right? This is exactly the same. Apply the projector on both sides. And then divided by the probability. If so, that there is no square here, no square root here. Or if I just think of a state vector, then I have square root here, just because it's this thing is density operators is quadratic in state vector. This also have some names called the Luder rules for some historical reason. This is of course the generalization of Born rule to mixed state. Born. Well, for time evolution or transformation, here, since if I have a pure state, then I would stick the unitary operator on this side, right? So that's how you remember it. This is, in particular, this is opposite to evolution of operator in the Heisenberg picture. If I remember correctly, that's here's like U dagger U, here's U dagger. It's kind of important too that so if U is generated by some Hamiltonian, so then the Schrodinger equation become this. Let me check. Recalculate it, but yeah, let me check. And yeah, this is supposed to be opposite of the Heisenberg picture as well. Yes. Maybe just a remark. Heisenberg picture, time evolution is the opposite. So like if A is some operator, some observable, yeah, it's you put it on the opposite side of here because this is for state, this is for state, this is for observable. Right? All right, and then we want to introduce some new rule that we're gonna use moving forward. Is that the joint Hilbert space of multiple system. So if you have two systems and those are described by Hilbert space A and B, then the joint Hilbert space is tensor product. And yeah, I hope you're sort of already familiar with this, right? So the dirty way that physicists define this is just through a basis. For example, if I have an O and B for the Hilbert space A, and then I have another basis for Hilbert space B, and this can have different cardinalities. Right? So maybe J's go to N, K goes to M. Then an orthonormal basis of the joint Hilbert space would be an Nm, a set of size Nm, N times M, right? Yeah, so J's go from 1 to N, K goes from 1 to M. And this would be, then you, in this way, you construct the whole Hilbert space by just taking all linear combinations of this basis vector. The abstract math way is that the tensor product space, so I'm not going to go into detail, but yeah, we can talk later if some of you are interested. So, and you can find this on like Wikipedia page as well. The tensor product space is kind of like an optimal is the oh, you can put D as well. Is in the end they're all equal. The optimal Hilbert space or vector. This is true for vector as well, even if you don't have inner product. Yeah. Is an optimal vector space. So it's kind of like smallest vector space, such that if I want the map from map from both A and B to be linear in both space. So in sense, if I want bilinear map. Okay. So if I have two vector space, each of them, so transformation in each of them are linear maps. And so if I want to consider them together, I can think of like a set of like bilinear maps. And the tensor product space is defined in such a way that every possible bilinear maps here are represented by linear maps on H tensor A tensor B. And so once we do that, it means that now we sort of don't have to care about like whether something is bilinear or linear. So we're just come back to the setting of linear maps that we're. And of course, if you have more than two vector space, and you have multilinear maps. And this is sometimes is the way that people define like tensor in general relativity, like they're like by multilinear map, whatever. Yeah. All right. Yeah. So those are the. Are these complete? I think that's all. So yeah, we have these axioms for now. The state, we just changed the definition of state to extend it to density operator. And something to look forward to now if you, okay. How to see this? So this time evolution, if you start with pure state, then you still end up as pure state, right? Clearly. So this is new pure state. And so you may wonder, well, then what about transformation between that turn pure state into mixed state? Or I don't know, mixed state into pure state. And yeah, we will encounter them later, maybe like in September. Yeah, yeah. Because now we can talk a lot about these, about this entanglement. Since okay, so here in this Hilbert space, you will have vectors that are product of, so the product from different vector space, and then you can separate them, right? So sometimes this is called what's supposed to be called a product state. But since you are allowed to take and you can think of this as basis vector as well. So I can always, if I have a state of this form, I can always take the basis in which I is one of the O and B of the first Hilbert space, and phi is from O and B of the other. But of course, you can take linear combination of product of basis. And so you have state that I have not defined like what are these guys. So of course, I cannot prove that it's entangled or product state. But you have general like something like this that cannot be reduced to this form, and those are entangled states, and that's where a lot of weirdness come from, right? Right. So before we end today, let's do 20 minutes. Any questions, any comments, any happy noise about this? Yeah, we are now go to newer version of quantum mechanics. We update the patch. Mm.
In this the axiom of quantum mechanics, so we use this or one for this.
We use a newer patch, right, which we haven't encountered yet. In particular, yes, the measurement will be generalized to POVM. and the time evolution will be generalized to completely positive map. It's just a name, right? Yeah. Tensor product is still true. Yeah. Yeah. But of course, when we talk about axioms, right, there can be different axioms that are equivalent, right? Depends on where do you want to start from. And so you see some kinds of paper that's like, oh, quantum mechanics actually only need two axioms because the third axiom is a consequence of something. Yeah, so people are still doing research about axioms, but mostly well, why? Because people that are doing research about axioms, they do not think only of quantum theory or classical theory. They think of all space of all possible theory, and they try to find some axioms that single out quantum theory as the preferred theory of nature, right? Because this is basically asking why is quantum theory true, right? In sort of a theoretical, like motivated way. Because if you usually if you ask some teacher or professor why is quantum mechanics true, they would just answer, well, idiot, because it's consistent with experimental result, but of course it's not the deepest answer because there can be many theory that are compatible with experimental results that we see so far, right? In particular, yeah. So in some sense, like in the first few weeks, that for example, when I provide like a derivation of probability by betting, so you can imagine something like that for quantum theory as well. And after I talk to you about that maybe there's no quantum way to do this, and I search Google, and in like 2021 there's someone who there's some paper in Physical Review A that claim that they can derive quantum mechanics from betting, and I leave it to you if you're interested in that kind of thing. Yeah. Right before we end this part, I want to talk about some particular mathematical theorem that will come back again when we talk about entanglement too. Is the relationship between the degree of freedoms of different ensemble decompositions. So basically, how many oil is infinitely many ensemble decomposition are possible, but how are they related? This is called the Schrodinger GSW theorem. Well, there's some different convention about this. Sometimes there's 4 people, sometimes there 5 people, sometimes there 3 people. So let's just make sure that SJW. Okay, right. So, but if I think if you go to Wikipedia, it's like SJGW or something. So many people, and I think this is maybe Hood, Wouters, Josa, and yeah, some from some famous name that I forgot. Right. Josa is of course of the Deutsch Josa algorithm fame. Wouter is also a great guy. I met him, but I did not meet Schrodinger. So the interesting thing is that Schrödinger already discovered this relation, but he already thought about this kind of thing, like freedom of ensemble decomposition, actually in relation to entanglement in the 30s, so like 1930s. And when people start to think about quantum information, we rediscover it multiple times. Actually, this is sort of some recurring theme of quantum informations. And something like the no cloning theorem has been discovered before. It's called a no cloning theorem, something like that. Right. So what does this say? So before I write out the statement, I can, let's see. Okay. So when I talk about the ensemble, rather than just thinking of these set of pure states as ensemble, to be precisely correct, like we should think of the probability too, right? The same as in statistical mechanics, which when people say ensemble, I would think of both like the support of the distribution, which are the state, and also the shape of the distribution. And for simplicity, so when I say that rho has this ensemble decomposition, I would also write it in terms of maybe I would use alpha, but that's fine. Is sometimes it's more convenient to write it in terms of unnormalized vectors when I already put the square root in the state. And another nice thing about this, other than not having to write the pj, is that now the sum is only in the support of rho, right? So the non-zero eigenvalue subspace, because when I multiply the pure state by zero probability, it disappears from the sum. So, but also because of that, I can now write an ensemble decomposition just by this set. And so the statement of this theorem relates to different ensemble decompositions. To ED, give the same density operator if and only if there exists unitary, possibly non-square matrix U such that this U is used to transform one vector in the ensemble to another. So yeah, that's fine. U alpha beta sum over beta. And why is this possibly non-square? Well, because different ensemble decomposition don't have to have the same number of elements, right? You can make a combination of any terms, even infinity. For example, in homework 3.2, you'll be asked to find ensemble decomposition of some qubit states from a set with different cardinalities. And then one part of the problem is to ask, well, how can you write this particular rho in terms of all states on the surface of the Bloch sphere? Something like that. So here's a proof. So this is an if and only if statement, right? So I have to prove both directions. So the easier direction is to assume first that you have the unitary matrix, right? And is this easy direction is this direction, right? So here the arrow I just made it is goes from if, right? So here to here. So if I assume that there's unitary matrix, then I show that these two give the same row. And if in the opposite direction, then I just use the opposite arrow. Okay. Right. So yes. So if I use this assumption, then I can first write rho in terms of psi of phi. Yeah. And then you can use that equation. Now there'll be two more indices to sum over. So the first one, well, just to not be confused, I think, not be confusing. Okay. Then it's important that this is not dagger. This is not, there is no transpose here because u alpha gamma is just a complex number. So let's see if it works. So I want to sum the common indices of this u to check whether it's unitary. Right? If I get the Kronecker delta back, beta gamma, alpha. Oh, sorry, not checking whether it's unitary, but this direction we already assume, yeah, it's unitary. Otherwise, it doesn't work. Okay. And this is the product. Maybe it's easier to see if I do it here. And if I want it to be a matrix product, then I want to transpose these. But then if I do that transpose and actually, then this becomes a dagger. Complex conjugate transpose U dagger U. This is the identity. It's important that this is identity in whatever the so here maybe you have to assume some kind of direction when I define this. just because let's see if I okay. If this is the space of like decomposition, ensemble this decomposition phi, and this is psi. So let's say if psi the decomposition here has more terms, right? It means that if I map it by U, then I will only map it to some subspace, right? And then if I apply a U inverse, then I can get back to the same thing. And so this identity is the identity in the smaller space. Whereas, so U dagger U is the identity. But the other way may not be true, right? Because if I, this map is, when I define it, it would be defined over all of this space. But if you don't want that, then you just pad all the like with 0 columns or 0 row over here. Right? But if you don't do that, if it's defined non-trivially on the whole of this space, then when I map this to here, then necessarily some of them would be in the kernel, right? Would go to the 0 vector, and so. But if that is the case, then it cannot be unitary. Unitary doesn't have a kernel. But anyway, yeah, this is fine. Maybe you have to be careful about direction a bit. Okay, now that was the easier direction. Here, now I want to prove that if there are two ensemble decomposition, then we can write unitary matrices here. But we will make our life easier by using the fact that there's already a sort of a preferred ensemble decomposition when we do calculation, which is the eigen decomposition of rho. So for example, if I want to go from, maybe it's like that direction, if I want to go from here to here, I can do that by going to the ensemble decomposition first, where each of these is just eigenvectors of rho that are not normalized, because I multiply by the eigenvalue, the square root of the eigenvalue, right? So going from here to here, I can go to here first, something like that. So if I can prove that you can go from the eigenbasis of rho to other decomposition with a unitary matrix, and we are good to go. Okay. So let's do that. Right. So first, let's just note here, right, that we write this in the eigen decomposition of rho. Now, so if I want to decompose, to write this in a different basis, here would be the eigenbasis, then I would just, since this is an orthonormal basis, right? Or I mean, if it's not complete, right? If the rank is less than the whole space, then I have to add vectors for it too. But that's fine. You can choose to add anything that's orthogonal to the support of rho. So I would, okay. But importantly, for this to be true, this has to be normalized, right? Yeah, so this, so complete this set to an orthonormal basis. And I do this, and this is sum over J. And now I want to, since we are gonna extract the unitary matrix that transform between these two, which somehow has to involve this coefficient, right? But the statement of the theorem is a unitary matrix between unnormalized vector. So I have to pull the lambda out of EJ first. So I've got EJ bar with this thing below, and then I would define it as let's see, it's kind of weird because it's mixed Latin index and Greek index, but that's fine. And now we want to show that this is unitary. So we do the same. Okay, what is the way that I do it? Alpha K. Again, the way that this works is the same as this, right? And then I just write it out, the definition. So I will get EJ on the left side, and on the right side I get EK, which doesn't depend on alpha, so I can pull alpha inside. Of course, there's this guy as well. And then here I get the outer product. But then this is just rho, right? And therefore, now since the EJ and EK are eigenstate of rho already, which are all orthogonal, then this is just delta JK. Because here I would have that sum of in the eigenbasis, right? Right. Oh yeah, and this is, I guess, the important reason why we use the eigenbasis, because if I'm trying to, oh, that is fine, that's fine, because we already assume that this is an ensemble decomposition of rho. Right? So right, so you can see this, why this is true. Okay. Because if I write in the eigenbasis, so I need another index. Yeah, let's use this. And then when I sandwich it, and then I have lambda L as well. So this will give the we make sure that I only I get the delta JK, right? Yeah, so JL and LK, and then it's come to JK. But then I divided the whole thing by this as well. But when I set J and K to be equal, then this cancel with that. Okay, so there you go. That's the degree of freedoms of the whole degrees of freedom of, maybe there's more, of doing the ensemble decomposition. And we ran out of time. We went past the time. So yeah, thank you for coming to class today. สัปดาห์นี้เรียนพฤหัสอีกวัน แต่ว่าสัปดาห์หน้าเป็นอังคารกับพุธ เพราะว่าพฤหัสมันมีไปทำแผนต่างจังหวัดอาจารย์เกือบทั้งวิทยาลัยก็จะหายหมดเลยครับ